Machine learning, ML, has revolutionized the way computers learn and make decisions without being explicitly programmed. From personalized recommendations on streaming platforms to real-time fraud detection in banking, ML is powering intelligent systems across industries. However, the effectiveness of these systems hinges on the type of ML model used. This video explores the main types of machine learning models, how they work, and when to use them. Machine learning is a branch of artificial intelligence, AI, that enables computers to learn from data and improve their performance over time without human intervention. The goal is to create algorithms that can identify patterns and make decisions with minimal human oversight. The ML process generally involves data collection, pre-processing, model selection, training and validation, evaluation, and deployment. The backbone of machine learning lies in the models, mathematical algorithms that process data and make predictions or decisions. ML models are broadly categorized based on the nature of the learning process. Supervised learning is when the model is trained on a labeled dataset. It learns to map inputs to the correct outputs. Examples include spam detection, image classification, and predicting house prices. Algorithms used in supervised learning include linear regression, decision trees, support vector machines, SVM, and neural networks. Unsupervised learning deals with unlabeled data. The model tries to find hidden patterns or groupings in the data. Examples include customer segmentation, anomaly detection, and dimensionality reduction. Algorithms used in unsupervised learning include k-means clustering, hierarchical clustering, and principal component analysis, PCA. Semi-supervised learning is a hybrid approach where a small amount of labeled data is used along with a large volume of unlabeled data. Use cases include speech analysis, medical imaging, and web content classification. In reinforcement learning, agents learn to make decisions by receiving rewards or penalties for their actions in an environment. Examples include robotics, game AI, and self-driving cars. Key elements of reinforcement learning include the agent, environment, actions, and rewards. Let's break down some popular models and how they work. Linear regression is used to predict continuous values by establishing a linear relationship between independent variables and a dependent variable. Logistic regression is used for classification problems and models the probability of a certain class using the logistic function. Decision trees are used for classification and regression by splitting the data based on feature values into branches. Random forest is an ensemble model that builds multiple decision trees and combines their results. Support vector machines, SVM, find the hyperplane that best separates the classes in a high-dimensional space. Naive Bayes uses Bayes' theorem with the assumption that features are independent for classification problems. K-nearest neighbors, KNN, predicts the output based on the majority of its K nearest neighbors. K-means clustering groups data into K clusters by assigning each data point to the nearest cluster center. Hierarchical clustering groups similar objects in a hierarchy by either merging or splitting clusters based on distance metrics. Principal component analysis, PCA, transforms original features into a smaller number of components that explain most of the variance. Neural networks consist of layers where each neuron applies a weighted sum and activation function for complex function approximation. Deep learning is an advanced form of neural networks with many hidden layers capable of learning intricate patterns in large data sets. Key evaluation metrics vary by model type. For classification, metrics include accuracy, precision, recall, F1 score, and ROC-AUC. For regression, metrics include mean absolute error, mean squared error, and R-squared. For clustering, metrics include silhouette score, Davies-Bouldan index, and adjusted RAND index. Choosing the best model depends on several factors, including the nature of the data, type of task, size of the data set, interpretability, and computational cost. A quick guide for task types and recommended models includes binary classification with logistic regression, SVM, and random forest, multi-class classification with naive Bayes, decision tree, and neural networks, regression with linear regression and random forest, clustering with k-means and hierarchical clustering, dimensionality reduction with PCA and autoencoders, time series forecasting with RNNs, ARIMA and LSTM, NLP with transformers and RNNs, and image processing with CNNs. Machine learning models are the engines behind today's smart systems. Understanding how each model works and when to use it is crucial for anyone working with data. Whether you're classifying emails, predicting customer churn, or generating realistic images, there's a machine learning model tailored for your task. From simple linear regression to complex deep learning architectures, the diversity of models ensures that there is always a right tool for the job. The key is to start with a clear understanding of your data and your goals, and then choose the model that best fits your problem. As machine learning continues to evolve, staying informed about the latest model architectures and techniques will be essential for leveraging its full potential.